lesson, we're looking at symbols of elements. Now, we know several elements have been discovered, and these elements are usually represented by a unique chemical symbol. Now, the use of symbol to represent element was first suggested by a man known as Berzelius in 1814, and then the elements known were represented by using the first letter of the name of each of the elements. So for example, H was used for hydrogen, S for sulfur, O for oxygen, and C for carbon. So as more elements were discovered, in a situation where the first letter has been used for another element already, then a combination of the first letter and any other letter from the name of the element was adopted. For example, when calcium was discovered, we cannot use C to represent calcium since C has been taken by carbon. And so the first letter of calcium, which is C, plus the next letter A, was used to represent calcium. Also, helium, which starts with letter H, but H has been taken by hydrogen, and so for helium, a combination of H and the next letter was adopted. The same thing applied for chlorine. Chlorine starts with letter C, but C has been taken also by carbon. Then a combination of the first letter of chlorine, which is C, and a letter from the name L was adopted, meaning chlorine is Cl. So that is how the symbols of these elements were formed. Initially, they choose the first letter of the name of the element, and in a situation when when the letter is already used for an element, then a combination of that first letter and any other letter from the name of the element was used. Also, there are few elements that derive their symbols from their Latin names. For example, elements like sodium, iron, copper, and silver, and gold derive their symbols from their Latin name. We have a table here showing the name of the element, the Latin name, and the symbol. So sodium, for example, in Latin is natrium, and so the symbol is Na, just like we use here. That is Ca, which is the real name of calcium, C for the first letter, and a letter from the name. So in this case now, we are taking the first letter of the Latin name plus the next letter from the name, so that the symbol of sodium is Na from the Latin name natrium. The same thing applies to iron. The Latin name is ferrum, and so the symbol is Fe, the first name plus the next name, the first letter rather, plus the next letter. Then copper, the Latin name is cuprum, therefore the symbol is Cu. Silver, the Latin name is argentum, and therefore the symbol is Ag. Tin, the Latin name is tannum, and therefore the symbol is Sn. Then gold, the Latin name is aurum, and therefore the symbol is Au. So in summary, some elements get their unique symbol from the first letter of their name. Then where the first letter is already used, the first letter plus any other letter from the name. And then a few of them get their symbol from their Latin name. Also the first letter of the Latin name and any other letter from the Latin name. The combination. Note here that the first letter is always written in capital letter, while the next letter is written in small letter. So you can write CA, that is C capital, and A capital to represent calcium. That will be 100% wrong. The first letter must be capital, the next letter must be small letter. Also, you can write small letter, then the next one also small letter. That is not correct. The first must be capital, the next must be small letter to represent the symbol of that element. Okay, just like we have symbols for element, we have formulae for element and compound. Now it becomes a formula if it's a molecule. For example, we said in a previous lesson that some element cannot exist as a single atom. In other words, they have to combine two or more atoms to form molecule. And so while we use symbol for atoms of element, we use formulae for molecules of element or compound. So a molecule of a substance is represented by the symbols of its component element. Such a representation is known as a chemical formula. Where an element exists as a molecule, a number representing its atomicity is written as a subscript after the symbol of that element. For example, hydrogen is always written with a 2 in front of it to show that hydrogen always, as a molecule, has two atoms. The same thing applies to oxygen, the same thing applies to nitrogen, the same thing applies to chlorine. All of these elements with a 2 in front of them indicates they exist as diatomic molecule. They combine two atoms before they can exist as a molecule. So this is a formula of the molecule of hydrogen. When it is H, that is when you say it's a symbol, but H2 here, that is a formula of a molecule. So for molecule of compound, which contains number of atoms of the component element, to write the chemical formula of a compound, there are steps we need to take in writing the chemical formula of the compound. Step number one, you write the symbols of the component element as a group. Then the number of atoms of each component element is also written as a subscript after the symbol of that element. For example, the formula, the molecular formula of sodium hydroxide is always written as NaOH. Na, which is the symbol of sodium, then O, the symbol of oxygen, H, the symbol of hydrogen. But in this case, the OH is a group, which is a hydroxide group. So here we have one atom of sodium, one atom of oxygen, and one atom of hydrogen. And the molecular formula of calcium triisocarbonate 4 is also written as CaCO3. Ca for calcium, C for carbon, then O3 for oxygen. So the point here is, while we talk about symbols of element, we talk about formula of molecules of compound. Symbol is used for what? Atoms of element. But when you talk about molecules of substances, it's not symbol. This is a formula, a chemical formula. The group of atoms like triazonitrate 5, hydroxide group, triazocarbonate 4, and ammonium are known as radicals. And what is a radical? Group of atoms that behave as a single unit. Whenever these radicals react, they act as a single unit, even though they are a group of atoms. For example, in triazonitrate 5, look at it, we have several atoms there. One atom of nitrogen and three atoms of oxygen. But whenever it reacts, it acts as a single unit. So such a group of atoms that behave as a single unit is known as a radical. So when more than one unit of radical is represented in a molecule, we write the formula by enclosing the radical within parentheses. What does that mean? Calcium hydroxide, for example, is written as CaOH, then 2. You can see the group OH is enclosed in a parenthesis because here in calcium hydroxide, you have 2 of OH group. That is the meaning of that. When more than one unit of radical is present in a molecule, we write the formula by enclosing the radical within parentheses. So for calcium hydroxide, you have more than one hydroxyl group. And so we enclose the hydroxyl group in a parenthesis, then indicate the number of it present in that chemical formula. So the table below shows some common compounds and their molecular formula. The first one here is hydrochloric acid. Hydrochloric acid, the formula is HCl. There is one atom of hydrogen and one atom of chlorine. Water, the formula is H2O. The software I used to bring this on the board does not support subscript and superscript. That's why the formula is not appearing here. So H2O is the formula of water, two atoms of hydrogen to one atom of oxygen. Ammonia is NH3, that's one atom of nitrogen to three atoms of hydrogen forms a molecule of ammonia. And carbon dioxide is CO2, and lead-2 oxide, lead-2 chloride rather, is Pb for lead, then chloride, Cl2, because it's lead-2 chloride. You see where the 2 is coming from when we talk about valency and how to write the chemical formula of a compound from the component element and from the component group. So calcium triisonitrate 5, that's CaCaNO 3, then 2. You can see here we enclose the NO3. Remember that NO3 is a radical. There is a group of atoms that behave as a single unit. And we said that where the radical in a compound is more than 1, we enclose the radical in a parenthesis and then indicate the number of times it is present as a subscript. So in calcium triazonate 5, that means this NO3 occur twice. So matter of fact, this 2 is coming from the valency of calcium. We are going to learn that as we progress. Then zinc tetrasulfate 6, this chemical formula is ZnSO4. So ZnSO4, that's zinc tetrasulfate 6. Okay, as we progress, we're going to learn how all of these come about. That is how to write the chemical formula for a given compound from the component elements or from the component atoms and the component radicals. Okay, so that is that for chemical symbols, chemical formulae, and chemical symbol. So summary, when we say symbol, we're talking about symbols of atoms. But formulae, we're talking about formulae of molecules of substances, either molecule of element or molecule of compound. And particle in terms of size, mass, and quantity. Now, the size of a molecule, how do we determine the size of a molecule? Now, recall that we say molecule is the smallest particle of a substance. Now, the substance could be an element, it could be a compound. Now, this molecule is so small that the naked eye cannot see it. Now, how can scientists then prove that they exist? Even when we cannot see it with the naked eye, even the powerful microscope, the electron microscope, which can magnify an object up to 200 times the size, the normal size of the object, cannot see the size or cannot determine the size of the molecule. The what makes scientists to believe that molecule actually exists if the naked eye cannot see it and the electron microscope cannot also see it. The size of a molecule is so small that it can be viewed as a film, a thin film or thin layer of a drop of oil on water surface, the thickness of which is about n times 10 to the power of negative 7, where n lies between 0 and 10. So something that is so small of that size cannot be seen with the naked eye and also cannot be seen with the electron microscope. However, we believe that they exist because we can feel their impact in chemical reactions and other occurrences in nature. So relative atomic mass of an atom. Early scientists expressed the mass of atoms as a ratio by comparing the mass of one atom of any element with the mass of the hydrogen atom. Now, the smallest or the lightest known element is the hydrogen atom. So because of that, early scientists use it as a standard by comparing every other element that has been discovered to the mass of hydrogen atom. Now, an arbitrary number was assigned to hydrogen because it's the lightest element, and that number is 1. The hydrogen atom was assigned a mass of 1 so that every other atom of every other element is compared to the number of times it is heavier than the atom of hydrogen. Now, what do I mean? Hydrogen as an atom was assigned a mass of 1 so that if any other element, let's call it element X, is discovered. Now, to know the mass of element X, we compare it, how many times is it heavier than hydrogen? So let's assume it's 10 times heavier than hydrogen. That means the mass of X is 10. Then another element is discovered. Let's call it element Y. Then we compare it again to how many times is heavier than hydrogen. If it is 13 times heavier than hydrogen, that means the mass of element Y. Early scientists or early chemists, and that standard is hydrogen, which was assigned a mass of 1. So the mass of an atom or the relative atomic mass carries no unit because it's a comparison. When you say something is relative, you are comparing the mass of one thing with the mass of another thing. So if hydrogen is 1, then another element is 10. That is the number of times that that element is heavier than hydrogen. In other words, you are dividing the mass of that element by the mass of hydrogen. Of course, the units are going to cancel out. So in essence, relative, anything relative does not have a unit. because it's a comparison. So the relative atomic mass of oxygen was found to be 16 times that of hydrogen. Remember that hydrogen is assigned a value of 1. So when oxygen was measured, it was 16 times the mass of hydrogen. And so it was assigned a relative atomic mass of 16. Sodium was measured. It was found to be 23 times heavier than hydrogen. And so it was assigned a relative atomic mass of 23. So all the elements in the periodic table were compared to hydrogen then, that is the ones that were known then, to be assigned their relative atomic masses. However, nowadays, the mass of atom can be measured very accurately using the mass spectrometer instead of a rough comparison with hydrogen, which was assigned a value of 1. If you want to know the accurate mass of atoms of elements in our today world, we can use an instrument known as mass spectrometer, so that the mass of hydrogen is now known to be 1.67 times 10 to the power of negative 24 gram. Now, 0.67 times 10 to the power of negative 27 gram is the mass of hydrogen, the actual mass of hydrogen. And of course, this number is far, far smaller than this arbitrary value that was given as 1. So this is the actual mass of hydrogen. This one is just an arbitrary value then, because this is the lightest element that is known to man. So they assign a value of 1 to it and then compare every other element to it as a standard to determine their relative atomic masses. Nowadays, we make use of an instrument called mass spectrometer, to determine the actual masses of these atoms of element. The that of hydrogen is this. Oxygen is 2.66 times 10 to the power negative 33 gram. See, again, far, far smaller than the arbitrary value of 16, which was obtained by comparing to hydrogen, which was assigned a value of 1. Then because oxygen is 16 times heavier than hydrogen, and so it was given an arbitrary value of 16 as its relative atomic mass. But the actual mass using mass spectrometer is 2.66 times 10 to the power 23 gram. So the mass values are too small to be practical in our day-to-day use as chemists. So because of that, we still make use of the relative atomic mass to calculate and to do a whole lot of things even today, because these actual masses are too small. Look at 2.66 times 10 to the power negative 23 gram. That is very, very small. So instead of making use of these actual masses, we still make use of relative atomic masses today. The mass spectrometric studies show that the atoms of most elements exist in more than one form known as isotopes. We mentioned isotopes in our previous class when we were talking about Dalton atomic theory. Most elements exist as isotope. Perfect example is chlorine, which always exists in chlorine 35 with a relative atomic mass of 35, and chlorine 37 with a relative atomic mass of 37. Apart from chlorine, carbon also exists in isotopes form. You have carbon 12, which is the most abundant. And then you have carbon 14 also. Then oxygen also exists as isotopes. Sure, most atoms today have their isotopic form. And so because of that, the relative atomic masses of most elements are not whole number because of the presence of isotopy. Okay, so each isotope of an element has its own mass, known as the isotopic mass. The atomic mass of an element that exists as isotopy is actually the weighted average isotopic mass of all the isotopes of that element. And this applies to the relative atomic mass of that element. And so that is the reason why most of them are not whole number. You see that the value is point something. For example, chlorine, the relative atomic mass is always 35.5 because of the presence of isotopy. Now, how is this value obtained? The relative atomic mass of an element that have isotopic mass is usually obtained by what? The relative percentage abundance of each of the isotope. That is adding the percentage abundance of each of the isotope together will give you the relative atomic mass of that element. So because of that, the standard used for comparing relative atomic mass is also has changed. Initially, they used hydrogen as a standard, which was given an arbitrary value of 1. But now, because of the presence of isotopy, there have to be a modification by choosing an atom or element that exists as isotope also. And that atom is carbon 12. So that the current definition uses carbon 12 as a standard because carbon has two isotopes, carbon 12 and carbon 13, which is present in relative quantity by 98.9%. That is carbon 12. Then the other one, which is carbon 13, is a 1.1%. So in any sample of carbon, there's carbon 12, which is the most abundant in nature, and the other one is 1.1%. So that carbon 12 is now the standard for defining the relative atomic mass of other elements. It has been given the mass of 12 units. And so the modern definition of the relative atomic mass of an element is the number of times the average mass of one atom of that element is heavier than 1/12 the mass of one atom of carbon 12. So mathematically, we write the relative atomic mass as average mass of one atom of that element divided by 1/12 the mass of one atom of carbon 12. So that if we are to calculate the relative atomic mass of oxygen, for example, we will divide average mass of one atom of oxygen by 1/12 the mass of one atom of carbon 12. That is a modern definition of relative atomic mass. Unlike when it was a mere comparison to hydrogen that was assigned a value of 1. Now we make use of carbon 12 as a standard so that every other element now is compared to how many times is it heavier than 1/12 the mass of one atom of carbon 12. Okay, so that is relative atomic mass. Now, element. And when we talk about molecule, then it has to be molecular mass. So now what is relative molecular mass? Every molecule is composed of atoms. Hence, it also has a molecular mass. And this molecular mass will be obtained by what? Adding all the masses of the atom present in that molecule. So the mass of a molecule is very small. It is also expressed as a ratio of carbon 12. Hence, the relative molecular mass, which is denoted Mr, as M subscript R, is defined as the number of times the average mass of one molecule of it is heavier than 1/12 the mass of one atom of carbon 12. And remember that carbon is a monatomic element. So here we are using it as a standard, both for relative atomic mass and relative molecular mass, because one atom of carbon 12 is still the same thing as one molecule of carbon 12. Okay, so whether it is relative atomic mass or relative molecular mass, carbon 12 is still the standard. So how many times is that molecule heavier than 1/12 the mass of one atom of carbon 12? That gives the relative molecular mass of that molecule, whether it's a molecule of element or molecule of compound. Now, for molecule of element, compound rather, you can obtain the actual relative molecular masses by adding all the relative atomic masses of the elements present in that compound. Now, in some discussion, you may see relative molecular mass also referred to as relative or formula mass. It becomes formula mass when we are talking about things like charged particles also or radical. Okay, because you cannot say a molecule of a radical. Rather, we talk about formula mass of that radical. So, in some discussion, you may see relative molecular mass as also formula mass. That's the point I'm trying to make. So, like I say that for a relative molecular mass of a compound, we can obtain the value by adding all relative atomic masses. Question here that says calculate the relative molecular mass of limestone, and then the formula is given to us CaCO3. So now, in brackets, they give us the relative atomic mass of each of the component atom. Now, remember we said that even though now we can get the actual masses of this element using mass spectrometer, however, we still use the relative value, that is those obtained by comparing these atoms to how many times they were heavier than atom of hydrogen. So this value here given to us are the relative value, not the actual masses of this atom. The actual masses of these atoms are too small to be used in any calculation. So we use the relative value. So calcium is 40, that is 40 times heavier than hydrogen, which was used as a standard. Carbon is 12, and oxygen is 16. So to calculate the relative molecular mass of calcium carbonate, we add all the masses of the component atom. So that calcium carbonate becomes, we have one atom of calcium, and one atom of calcium is 40. Then carbon, carbon is 12. The value in bracket, that is what I'm using. While oxygen is 16. But in calcium carbonate, you have three atoms of oxygen. So this 16 is for one atom of oxygen. That means three atoms of oxygen. We're going to multiply this 16 by 3. So that will have 16 times 3, and that will be 40 plus 12 plus 16 times 3 is 48. Now 40 plus 12, that is 52. 52 plus 48, that is 100. So the mass of calcium carbonate is 100. The relative molecular mass. And recall that we say anything relative does not have a unit. So just write the value. There is no unit. The next example says calculate the relative molecular mass of sodium tetraisosopate 6. Given that sodium is 23, sulfur is 32, and oxygen is 16. This is a typo. Let me correct it. Is 16. Okay, so sodium tetraisopate 6 is Na2SO4, meaning there are two atoms of sodium in sodium tetraisopate 6. Now, if one atom of sodium is 23, the two of them will be 23 times 2. We have 23 times 2 plus sulfur is 32, and it's only one atom here, so plus 32. Then plus oxygen is 16. In sodium tetrasulfate, there are four atoms of oxygen. That will be 16 times 4. 23 times 2 is 46. Then plus 32 and plus 16 times 4, that's 64. Adding all this together, let's use a calculator to make our work faster. 46 plus 32 plus 64, 42. Again, there is no unit since we are talking about relative molecular mass. It's just the number of times it is heavier. Then this is the relative formula mass of aluminum is 27, sulfur is 32, and oxygen is 16. Now, if you look at this question, the formula for aluminum tetrasulfate is not given to us, so it is left for us to write it by ourselves. Aluminium is Al, that's a symbol of aluminum. For us to be able to write the correct formula of aluminum tetrasulfate 6, we need to know the valency of aluminum. And the valency of aluminum is 3 plus. We are going to learn this in our next class. Valency is a combining power of an element or a radical. That is the number of electrons that is lost or gained when it undergoes chemical combination. So for that of aluminum, it is 3. Then tetraisopropyl is a radical, is a group, and the valency is 2, so SO4 and 2 minus. Now, for combination to occur, they have to exchange their valency. That is why we define valency as a combining power of an element. So aluminum is going to take these two from sulfate group, while the sulfate group will take the 3 from aluminum. Now, this marker is trying to control itself. I'm trying to finish drawing something. So by the time they exchange their valency, you have the formula like this: Al2, the 2 is coming from this sulfate, the valency of sulfate. Then SO4, we take the 3 from aluminum. And we said that in a situation where you have more than one radical, then the radical is enclosed in a parenthesis. Then the number of times that the radical appear is now written as a subscript. So since this radical SO4 is taking this 3 from sulfate, from what is it called, from aluminum rather, we put the 3 here to show that in aluminum tetrasulfate 6, there are 3 sulfate groups. So the correct formula of aluminum tetrasulfate 6 is Al2SO4, then bracket 3. Now the question says we should calculate the formula mass. Now, aluminum is 23. Here we have 2 atoms of it. Aluminum is 27 rather. Here we have 2 atoms of it, so that would be 27 times 2 plus sulfur is 32. These 3 outside here affect everything and close in the parentheses. So that will be 32 times 3. First of all, let's work on the bracket first and then leave the 3 outside, just like we used to do in board maths, right? So I'm going to place the 3 here because I'm going to use this 3 to multiply the value I'm going to have from this bracket. So that will be 3 times 32 plus, now oxygen here, there are 4 atoms of oxygen. One atom is 16, so the 4 of them will be 16 times 4. So that 27 times 2, that will be 54. Then plus 3 times 16 times 4 is 64. 64 times plus 32 rather. 64 plus 32 is 96. So 3 times 96. Again, let me explain that. This 3 is coming, this 3 here, because this 3 is outside the parenthesis, so it's affecting everything enclosed in the parenthesis. And recall that this SO4 is a group. And these 3 affect to that group, everything, all the atoms here. That is why we have to multiply it by the value. Now, adding all these atoms in the parentheses gave us this 96. So now this 3 times 96 is 288. So that will be 54 plus 288, which is 342. I the mass of aluminum tetrahydrosulfate 6.